we have proved 0. If y1 and y2 are solution of this differential equation, their linear combination c1y1x plus c2y2x is also a solution of this differential equation. Now next theorem, there exist two linearly independent solutions. Y1 and Y2 are linearly independent solutions. There exist two linearly independent solutions. Of which differential equation? This is associated homogeneous differential equation, second order linear differential equation. And which form? Associated homogeneous linear differential equation. So if y1x, y2x are two linearly independent solutions, what is the speciality? These two are linearly independent solutions of this differential equation. A0x, y double dash x, a1x, y dash x, a2x, yx equal to 0. X is always in some interval a to b, open interval a to b. Such that now these two solutions are linearly independent solution of this differential equation, such that now they exist, two solutions, two linearly independent solutions exist, such that we have to prove this thing. It's every solution yx. So any other solution of the same differential equation may be written as c1y1 x plus c2y2 x. So if this is a third solution, then any other solution other than y1 and y2 of the same equation, then this is nothing but a linear combination of these two. That means this third solution can be obtained from y1 and y2 by taking their combination. So we will prove this result. Given differential equation is a0x, y double dash x, a1x, y dash x, a2x, yx. Right hand side is 0 in this second order linear differential equation, and x is taking value in this open interval a to b. Now let x0 be any point, take any point by existence and uniqueness theorem for this point x0, and for any two constants. So we are taking these two constants, c1 equal to 1, c2 equal to 0, 1 and 0. So what is the existence and uniqueness theorem? For any two constants, there exists a unique solution y1x. So for this two constant where c1 is 1, c2 is 0, for these two constant there exists a unique solution y1x of linear differential equation satisfying y1 x0 equal to c1, that is the value of this solution at x0 is c1, and value of the derivative of the solution at the same point x0 is c2. y1 x0 means value of the solution at x0, and y1 dash x0 means value of the derivative of that solution at the same point x0. This is c2, exist by existence and uniqueness theorem. So in this first case, we have selected which constant? c1, c2, c1 as 1, c2 as 0, and we will get a solution y1 for this linear differential equation such that y1 x0 is c1 and y1 dash x0 is c2. But c1 we have taken as 1, c2 we have taken as 0. Now one more set we will take c1. We will change the values of c1 and c2 now. Similarly, change the constant. Here we have taken 1, 0. Now take 0, 1. C1 is 0 and C2 is 1. For these two constants, again, by existence and uniqueness theorem, there exists another solution y2, because for any two constants, if you select any two constants, then there exists one solution satisfying such values. So for this two constant where C1 is 0, C2 is 1 now, there exists unique solution y2 such that, now this solution is such that its value at x0 is 0 and its value of derivative at x0 is 1. That is, this is your C1 and this is your C2. Value of this solution at x0 will be C1, C1 is 0, and value of its derivative at x0 will be C2, and C2 in this case is 1. So we have applied existence and uniqueness theorem for the two constants. Here the two constants are 1 and 0. Here in second solution the two constants are 0 and 1. Now, first part, let us prove y1x and y2x, which we have just written, are linearly independent solutions. How to prove two solutions are linearly independent? If you consider their linear combination and if you show that the two constants C1 and C2 are 0, that is, first of all, consider this linear combination C1y1x plus C2y2x equal to 0 and show that C1 is 0, C2 is also 0. Then by definition y1 and y2 are linearly independent. If you get both constant, value of the both constant equal to 0. We start with this linear combination. Suppose it is 0. Now let us find the values of C1 and C2. Now differentiate this equation. What do we get? C1 y1 dash plus C2 y2 dash equal to 0. So these are the two equations. In this equation, x is in the interval, open interval a to b. Replace this x with x0. We get C1 y1 0 plus C2 y2 0 equal to 0. And from the second equation, C1 y1 dash, because it holds for any point x in open interval AB, and x0 is a point in this interval. So let us replace x by x0. So C1 y1 dash x0 plus C2 y2 dash x0 equal to 0. So just replace in these two equations, replace x by x0. So we get these two equations. Now y1 is a solution for which C1, C2 we have taken 1 and 0. So y1 is a solution so that y1 x0 is 1 and y1 dash x0 is 0. Whereas for y2, C1 is 0 and C2 is 1. So it is a solution so that y2 x0 is 0 and y2 dash x0 is 1. This is by existence and uniqueness theorem. These two solutions exist. So from equation 2 and 3, what are the values of y1 x0, y1 dash x0, y2 x0 and y2 dash x0? Here we have written these values. Now y2 x0 is 0, so this value is 0, and y1 dash x0, so y1 dash x0 is 0. Now what remains in this first equation? C1 y1 equal to 0, C1 y1 equal to 0, but y1 is a solution, so we conclude that constant C1 is 0. Similarly, in the second, C2 y2 dash is 0, y2 dash is a solution, non-zero solution, so Therefore, C2 is 0. So we get C1 equal to 0, C2 equal to 0. So what we have shown, if we suppose that C1y1, C2y2, this combination is 0, then what result we get? C1 equal to 0 and C2 equal to 0. So C1y1 plus C2y2 equal to 0 implies that both constants are 0, and therefore, by definition, the two solutions are linearly independent. So two solutions which we have selected in this part are linearly independent solution. Next, to show that the every solution yx of equation 1 may be expressed as, now take third solution. We will show that this yx can be expressed as linear combination of y1x and y2x for some constant. This third solution we can write as a linear combination of y1 and y2. So let C1 and C2 are two constants and x0 is a point in open interval a to b. And for these two constants, by existence and uniqueness theorem, we get one solution. So C1, C2 are arbitrary, so yx is also a arbitrary solution. So let yx be a solution of 1 satisfying by existence and uniqueness theorem. Its value at x0 is C1 and its value of its derivative at x0 is C2. Solution is such that its value at x0 is C1 and value of its derivative at x0 is C2. This is by existence and uniqueness theorem. Now, let ux denote this yx minus c1 y1x minus c2 y2x. What is this? It is like this. 1 into y1x, 1 is a constant, minus c1 into y1x, 1 into yx, then minus c1 into y1x, minus c2 into y2x. So this is called a linear combination of three solutions. One solution is yx, another is y1x, and the third is y2x. These are the three solutions of differential equation 1. So let ux denote this linear combination. It contains yx, y1, y2, y2, its coefficient is minus c2, yx, this solution we have written as c1 y1 plus c2 y2. Take this y1 or take this term, the left hand side, we get yx minus c1 y1x minus c2 y2x. This we have written as ux. So let ux denote this yx minus c1 y1x minus c2 y2x. Right. Now what happened? We now show that this ux is 0. And if ux is 0, what will happen? This linear combination is 0, and we can write yx as c1 y1 plus c2 y2. We have to show that yx is a linear combination of y1 and y2. So we have to prove this result. So for that, let us consider this function ux like this. Ux is obtained from this equation yx equal to c1 y1 plus c2 y2, that is yx minus c1 y1x minus c2 y2x. This expression we take as ux. So ux is a linear combination of three solutions, and what we have seen by theorem 1, if you have two solutions, then their linear combination is also a solution, right? So similarly, we can prove a linear combination of three solutions is also a solution of the given differential equation. So by theorem 1, since a linear combination of two solutions is also a solution of one, Therefore, linear combination of three solutions is also a solution of one. Let ux denote this expression yx minus c1 y1 minus c2 y2. Now, ux is a linear combination of three solutions. Yx is a solution of one, y1x is a solution of one, y2x is also a solution of one. So their linear combination is also a solution of one. So ux is a solution of differential equation 1. Which differential equation? a0 y double dash plus a1 y dash plus a2 y equal to 0. This is equation number 1. So ux is a solution of this differential equation, second order linear differential equation. Now find out derivative of u. What is u dash x? It means derivative of y, which is y dash. C1 is constant, minus C1 is constant. Derivative of y1x is y1 dash x minus C2 into derivative of y2x is y2 dash x. So it is a simple derivative, derivative of u. So ux and u dash x. Ux is a solution of 1, first of all, because it is a combination of linear combination of three solutions of 1. So it is a solution of 1, first thing. Second thing, find out u of x0 and u dash x0. What is u of x0 in this equation? Put x equal to x0, we get y0 minus c1, y1 x0 minus c2, y2 x0. Right? But y1 and is a solution for which y1 is a solution for which what are the values? Its value at x0 is 1 and value of its derivative at x0 is 0. And for y2 is a solution of 1 for which its value at x0 is 0 and value of its derivative is 1. These are the solutions like this. So out of these two values, we require y1 x0, y1 x0 is 1. So we are using this value. And y2 x0, y2 x0 is 0. So we are using this value, it is 0. And what is yx0? Yx is a solution for which we have yx0 equal to c1. So yx0 is c1. y1 x0, y1 x0 is 1. We are using this value. Y2 x0 is 0. These three values we have used. So y of x0 is c1. y1 x0 is 1. y2 x0 is 0. So this term is 0. Now c1 into 1 is c1. c1 minus c1 is 0. So we get u of x0 equal to 0. Similarly, find out the value of u dash x0. U dash x0, what is u dash x? This equation number 3, put x equal to x0. We get y dash x0 minus c1, y1 dash x0 minus c2, y2 dash x0. Now substitute the values again. Y dash x0 is c2. Look at this equation. This is c2. Then y1 dash x0 is 0. This is the value. This is 0. And y2 dash x0, y2 dash x0 is 1. This is 1. So this is c2. This term is 0. c2 minus c2. This is 0. Y dash x0 is 0. So what we have done here, we have written one expression ux. This is ux yx minus c1 y1x minus c2 y2x. We have written one expression, and because it is a linear combination of three solutions, yx is a solution of 1, y1x is a solution of 1, y2x is a solution of 1. Because all the three are solutions of 1, this expression is a linear combination of three solutions of differential equation 1. And the theorem 1 says that if we have a linear combination of solution, then it is also a solution of 1. So ux is a solution of 1. This is a first result. And then we have shown that it is a solution such that u of x0 equal to 0 and u dash x0 equal to 0. That is in ux. If you put x equal to x0, we get 0. And in u dash x, if you put x equal to x0, we get 0. So it is a solution of differential equation 1 for which u of x0 equal to 0 and u dash x0 equal to 0. So thus ux is a solution of equation 1 satisfying u of x0 equal to 0 and u dash x0 equal to 0. So it implies that ux is identically equal to 0. That means it is 0 for all x. By corollary to existence and uniqueness theorem, this solution is identically 0 for all x. Let us see this corollary we are using. If yx is a solution of this differential equation 1, a0x y double dash a1x y dash a2x y equal to 0, yx is a solution of this differential equation satisfying its value at x0 is 0 and value of its derivative at x0 is 0. Its value at x0 is 0 and value of its derivative at x0 is also 0. Then in that case, this solution is identically equal to 0. That is, it is 0 for all x. So we are using this corollary. So ux is a solution of 1 and it satisfies this two condition. Its value at x0 is 0 and value of its derivative at x0 is also 0. So it is identically 0 for all x in A. But what is ux? Ux is this linear combination of three solutions yx minus c1 y1x minus c2 y2x. It implies that yx is equal to c1 y1x plus c2 y2x. So that is yx is a linear combination of c1 and c2 where y1 y2 are linearly independent solutions of 1 and yx is a third solution, any other solution of differential equation 1. It can be written as a linear combination of these two solutions y1 and y2 which are linearly independent.